Stellar black hole. A stellar black hole is born when a massive star runs out of fuel and collapses under its own gravity. In only a few seconds, an object larger than our sun can shrink into something only a few dozen kilometers across. The gravity becomes so intense that not even light can escape. What remains is completely invisible unless it pulls gas from a nearby star, heating that gas until it glows brighter than millions of suns. Most black holes in our galaxy belong to this family, silently drifting through space with almost no sign that they exist. Intermediate mass black hole. An intermediate mass black hole fills the gap between the smaller stellar black holes and the enormous giants found in galaxy centers. For years, astronomers were not even sure these objects existed because they were so difficult to find. Many are thought to grow inside crowded star clusters, where repeated collisions slowly build something much larger. Some may contain tens of thousands of times the sun's mass. Their discovery helped solve one of astronomy's biggest mysteries by showing how black holes can continue growing instead of stopping after a single star dies. Supermassive black hole. A supermassive black hole sits at the heart of almost every large galaxy, including our own Milky Way. These giants can weigh millions or even billions of times more than the sun. Surprisingly, despite their incredible mass, the region where matter disappears is often smaller than people imagine compared to the size of the galaxy around it. The black hole at the center of galaxy M87 was the first one ever photographed, revealing the glowing ring of hot gas around an object that cannot be seen directly. Without these enormous black holes, many galaxies might never have formed the way they did. Primordial black hole. A primordial black hole was never created by a dying star. Instead, it is a theoretical object that may have formed less than a second after the Big Bang, when the young universe was unimaginably dense. Tiny regions with slightly more matter than their surroundings could have collapsed instantly into black holes. Some might have been smaller than a mountain while weighing more than Earth. If any still exist today, they could help explain one of the greatest unsolved puzzles in science, the true nature of dark matter. Rotating black hole. A rotating black hole spins because the star that created it was already spinning before it collapsed. This rotation twists space itself, an effect so strange that nearby objects are forced to move along with the spinning fabric of spacetime. Around it lies a region called the ergosphere, where escaping becomes almost impossible without moving with the black hole's rotation. In theory, energy can even be extracted from this spinning motion, making rotating black holes among the most powerful engines anywhere in the universe. Micro black hole. A microblack hole is a hypothetical object so tiny that it could be smaller than an atom while still containing extraordinary mass. Some theories suggest these miniature black holes might briefly appear during extremely high-energy particle collisions. If one formed, it would evaporate almost instantly through a process known as Hawking radiation, disappearing before it could interact with anything around it. Despite popular fears, scientists have shown that such objects would pose no danger to Earth, but finding one would completely transform our understanding of physics. Binary black hole. A binary black hole consists of two black holes locked together by gravity. They orbit each other for millions or even billions of years while slowly moving closer together. As they spiral inward, they create ripples in spacetime called gravitational waves. In 2015, humanity detected these waves for the first time, confirming a prediction Albert Einstein had made a century earlier. The signal lasted only a fraction of a second, yet it carried more energy than all the stars in the observable universe combined released during that same moment. Evaporating black hole. An evaporating black hole slowly loses mass through Hawking radiation, a phenomenon that combines quantum physics with gravity. Contrary to the common belief that black holes only grow larger, they can actually shrink over unimaginable stretches of time. A black hole with the mass of the sun would survive for far longer than the current age of the universe, but eventually it would disappear completely. Its final moments may end in a sudden burst of energy, leaving behind no solid object at all, only radiation spreading into the darkness of space.